Hello everybody, and welcome to the very last part of this long section 1.2. So we are looking at, let's see, the bottom of page 14 in the workbook here. And we'd like to take this idea of a limit that we've been talking about and connect it to the concept of instantaneous velocity. Okay, so let's read this definition together. We'll let s equals f of t be the position of an object at time t. Then the instantaneous velocity, recall our notation, iv at t equals a is instant velocity at t equals a, can be calculated using either of the following formulas. Okay, and the first formula looks like this. It says we can take the limit as b goes to a of the average velocity over the interval from a to b. Now, what is the logic behind this formula? Well, instantaneous velocity is about the velocity at one value of t, and so what this is really saying is that if we want that instantaneous velocity at one point, we're going to start by taking the average velocity between a and b, and if we let b approach a, we're talking about an average velocity over a really small interval that's close to a, and that average velocity is going to approach the instant velocity that we want. Okay, and if we wrote this formula out in a little bit more detail, AV, the average velocity, is just rise over run graphically. Okay, so the whole formula would look like this. Okay, and then number 2 is just an alternate formula for calculating the same thing. We can also find the instantaneous velocity by taking this limit. Same idea. We're taking the average velocity over an interval between a and a plus h, and if h is small, if it approaches 0, then we're talking about a really small time interval where all of our time values are close to a. Okay, and if we look at this limit and wrote it out, it would look like this. Okay, and what we're saying is that we can use either one of these two formulas to calculate instant velocity. All right, so I'd like to do one example where we try this out. Okay, and this is we're gonna have to scroll ahead a few pages here. Okay, so all the way to page 18 here. Page 18. Let's read this question together. So it's referring back to example 1 on page 9. Okay, in that example, we had the height of an object that was fired into the air, and the height was given by the function 100t minus 16t squared. We're going to see if we can calculate the instantaneous velocity using the limit formula that we just wrote down. Okay, and they'd like us to do that at t equals 1 second. All right, well, let's see what that would look like. So the instantaneous velocity at t equals 1, by definition, is going to be the limit. I'm going to use the second of the two formulas. The limit as h goes to 0 of f of 1 plus h minus f of 1 over h. That's what we need to calculate here. Okay, and this is going to involve some algebra, so we'll start with the f of 1 plus h. So 1 plus h is an input value of our function. So what that means is that we're going to take 1 plus h, we're going to go to our formula for f, and everywhere that you see a t, you're going to put a 1 plus h. So we'll get 100 1 plus h minus 16 times 1 plus h squared. We just replaced both of those t's with 1 plus h's. Okay? And then we come to f of 1. And so same idea. This time we're going to take 1, and we're going to substitute it into our formula everywhere we see a t. So we're going to get 100 times 1 minus 16 times 1 squared. Okay, and all of that's divided by our denominator, which is just h. Oh, and actually, I made a little bit of a notation error here. There should be a limit sign in front of this, because we're taking the limit of this. Okay, it's important not to forget that. All right. So next line, now we're going to get a little bit intensively into the algebra here. So starting with the 100 times 1 plus h, let's distribute the 100 through. That's going to be 100 plus 100h minus 16 times, and then maybe we could FOIL that 1 plus h squared out. That's going to give 1 plus 2h plus h squared, if you multiply 1 plus h by itself. Okay, and then we come to 100 times 1 minus 16 times 1 squared. That's 100 minus 16 if you write it out. And 100 minus 16 happens to be 84. Okay, so I'll go ahead and just write that out. Okay, and continuing, let's see, we're going to get 100 plus 100h. We'll take that minus 16 and factor it through. So minus 16 times 1 is minus 16. Then we come to minus 16 times 2h. That's minus 32h. And then finally minus 16h squared minus 84 all over h. Okay, can we simplify that at all? Well, notice that we've got three constant terms, 100, minus 16, and minus 84. If you take 100 minus 16 minus 84, you're going to get 0. So all three of those numbers cancel out. Okay, and another thing that you might notice here is that 100h and minus 32h, those are like terms, so we can subtract those. So let's see, 100h minus 32h is going to give us, I believe, 68h. And then we've still got a minus 16h squared in the top. Okay, so quite a bit of algebra that we're doing here. Okay, do you notice anything else that we could do here to simplify this? Well, I see that there's an h that we can factor out in the numerator. So if we do that, pull an h out, we're going to get a 68 minus a 16h. And notice that now we've got an h in the top and the bottom, and those cancel. That's kind of a key step because we're going to be taking the limit here as h goes to 0. We need to get rid of that h in the denominator if we want to let h approach 0 and get a number out of this. All right, so we're almost there. After we cancel the h's, we're taking the limit as h goes to 0 of 68 minus 16h. And the only question left is, what do we get for that limit? Okay, well, h is approaching 0. So if we substitute 0 in for h, we're going to get 68 minus 16 times 0. No more 0 denominator to worry about. And that's just going to give us 68. Okay, units, since this is a velocity, should be feet per second. That's our answer. And there was one last thing that they asked us to think about. I'm going to just scroll back up. Does this answer agree with our estimate from page 9? I'll leave it to you to look back, okay, at page 9 and confirm that, yes, this does agree. This was the guess that we made as to what the velocity might be. Okay, so you can take a look at that and confirm it.